Okay, let's talk about capacitance. So capacitors are devices used to store charge and store electrical energy. That's the main thing you need to get from this. Capacitors store charge and they store energy. So the idea is, here's one configuration. This is called a parallel plate capacitor. And there are a bunch of different capacitors we can have, but basically we'll have two conductors hooked up to a voltage source with some kind of insulator in between the conductors. So when we hook up to the voltage source, we'll get some kind of current flow here. So we just hook this conductor up. Some charge is going to flow. What's actually going to happen is electrons are going to flow off of this plate into the battery. And here, electrons will flow out of the battery onto the other plate, leaving a net positive charge on one side and a negative on the other. That will create an electric field in between the plates, and we'll get charge stored on each of the plates. We could, if we wanted to, then quickly unhook the battery and we would just have charge stored here. That requires energy. The battery loses some of its potential energy, its chemical energy, in order to do this. We had to do work to get these charges here. That work could then be, or that energy could be converted back into work to run something. So like all of your electronic devices have a bunch of capacitors in them for storing up energy that it will use later, or for storing up charge. Okay, so if we had, say, a parallel plate capacitor, we know that we'll get a near constant electric field in between them. We'll develop our formula for capacitance here in this situation in a moment. First, the definition of capacitance, C, is the amount of charge you can store on the positive plate per volt applied. So Q here is the amount of charge over here. We're going to always end up with the opposite charge on the other plate, but when we're saying Q, we just mean the charge on the positive plate. And V is the voltage of our battery or our voltage source, whatever that happens to be. Capacitance then is charge per volt stored on the positive plate, and it's measured in farads, named after Michael Faraday. So 1 farad is 1 coulomb per volt. Here's some pictures of a bunch of different kinds of capacitors. These are cylindrical capacitors. These look like parallel plate capacitors. Okay, so say we have a parallel plate capacitor separated by some distance d. The area of each plate is A. We have a voltage source V here. As soon as we hook that up, that'll give us, well, after some time, this actually takes, we'll develop that once we get resistance, but this takes a microsecond to charge up this positive plate and this negative plate. Our electric field, we figured this out back when we did Gauss's law. The electric field in between those plates is sigma, the charge density, divided by epsilon naught, where charge density is total charge divided by area. We know, because we have a constant electric field, that the voltage difference across that plate is the electric field times the distance between the plates. So now just doing some plug and chug, we get V equals QD over epsilon naught A. And by definition, capacitance is Q divided by V. So that develops this formula for the capacitance of a parallel plate capacitor, epsilon naught A over D. Notice that it's a function only of the geometry. Capacitance only depends on the geometry of the situation. It does not depend on how much voltage or charge. Those are results. This physical situation has a particular ability to store charge. No matter what battery you hook up, The capacitor has a certain capacitance, its ability to store charge, that only depends on the distance between the plates and the area of the plates. If you put a bigger battery, you can store more charge. But the capacitance, the charge per volt, only depends on the geometry. Okay, and then this is all from your book. You can read through some of these examples. We could have a spherical capacitor. Here's the capacitance. You could read through all those details if you want. But the capacitance, the ability of a spherical capacitor to store charge, only depends on the geometry, does not depend on the voltage source you actually hook it up to. It depends on the two different radii of our concentric spheres. And similarly for a cylindrical capacitor. So there's the derivation. Here is the capacitance of a cylindrical capacitor. In a circuit, this is the symbol we use for a capacitor. This is the one I'll usually draw. These mean the same thing. I usually typically draw this. Notice this is different from a battery that we'll be drawing when we talk about resistors and direct current circuits. A battery will have a long side and a short side, and a capacitor, both sides are the same length. Okay, we're going to talk about capacitors in series and parallel in a different set of videos. I want to talk about here energy stored in a capacitor. So remember, that's the whole point of a capacitor, is it stores energy. It stores charge. Well, how much work is required to get those positive charges on the positive side and the negative on the negative? It's a pretty simple calculation here. This is how much work is required by the battery to move those charges. Now that energy is stored as electrical energy in those parallel plates or whatever capacitor we have. Notice this doesn't depend on the type of capacitor. This is for any capacitor. The energy stored is the amount of charge you ended up getting on the positive plate times the voltage applied divided by 2. Or, because remember C equals Q over V, we could write that in terms of Q and C. Or we could write it in terms of V and C. Okay, now in the real world, we like our capacitors to be better. So what we'll do is, I think it's easier to start here. We'll put something inside our capacitor. We'll fill that area up with, instead of a vacuum, some kind of insulating material. And what happens is we get polarization. We get some drift charge floating around inside that insulating material because we've got all these positives over on one side here. Some electrons will want to come over and hang out with those positives. Now remember, this is an insulator. They're not going to actually touch. We're not going to lose charge here. They'll just kind of hang out on one side of this insulator, leaving some positive charge on the other side. That creates an electric field. Got a good picture here somewhere. That points backwards in there. That decreases my total electric field inside the capacitor, which makes it easier to pump more charge onto the positive plate. It increases my capacitance. We call that material we're sticking in there a dielectric. So we've got our regular old capacitor with a vacuum in there. We stick a dielectric in there that creates an electric field that points in the opposite direction, which overall decreases our electric field. So for the same voltage now, we can pump more charge on here. we end up with a new amount of energy required that depends on this guy here called kappa. That's called the dielectric constant. And that's a constant associated with that material we're putting inside our capacitor. That changes the capacitance of our capacitor. We get the original capacitance times kappa, or dielectric constant. So here's a table of some dielectric constants. A regular vacuum has a dielectric constant of 1. So of course, that's our base case, right? If we have air inside our capacitor, it increases our capacitance by this factor. If we put, say, nylon in there, we increase our capacitance by over 3 times. We can store more charge per volt. It makes it a much more efficient capacitor. Glass is a very popular dielectric. Increases our capacitance up to 6 times what it was before. Okay, that's a good place to stop.